So today we are going to be talking about separation properties. So what this means, we're basically going to be talking about different conditions that a topological space can have, in which separation property basically means just being able to separate points or closed sets from each other using open sets. And so these separation properties are going to be, they all have names, but they're most commonly denoted by these like letters and numbers, right? So T1 is going to be the first separation axiom or separation property. And this basically says that if P and Q are distinct points in a topological space X, then there exists an open set U, or really, I think, is this open sets plural, U and V, which contain P and Q, but not the other. So what this means, of course, this definition, I wrote it kind of sloppily, but I can describe better via a picture, is that if P and Q are your points, then there are open sets U and V, such that U contains P but not Q, and V contains Q but not P. Now notice these open sets might intersect, and that leads to the next separation axiom, which is T2, but this one we commonly use the full name for this, which is the Hausdorff. We say that if our topological space has this property, we say X is Hausdorff. And so, like I said, all of these properties are going to have, they're going to be named after mathematicians, but really this is the only one that gets its name used. So in this one, it's pretty much the same, but for points P and Q, there exists disjoint open sets UV, right? So in this case, here's your 2 points, P and Q, right? Then we can always find open sets that are disjoint, right? Such that U contains P and V contains Q, and they're disjoint, right? And so notice, if they are disjoint, then that automatically implies that, if U and V are disjoint, and I know that P is in U and Q is in V, that automatically tells me that Q is not in U and P is not in V. So in particular, if you know that a space is T2 or Hausdorff, then you automatically know that it is T1. And a good theorem to prove, or just it's not really a big result, but is that T1 is equivalent to the condition that all 1-point sets are closed for all P in X, right? And the reason this is, or like the way you would prove it is by trying to show that P is its own closure, right? And again, the way that you would show this is by showing that for any Q not equal to P, right? I know that I'm going to have these sets U and V, right? So here's P, here's Q, and then X minus V is closed, contains P, and not Q. But the closure of this set must be contained in X minus V, right? Because the closure of P is going to be contained in any closed set which contains P, so this means that Q is not in the closure. And this works for any point that is not equal to P, and so therefore the closure of this set must be itself, right? The next thing is sort of a generalization of this. So if X is T1, U is open, and P is an element of U, then U minus P, right? If I take P out of U, then this is still an open set. So this is a generalization. Here we're basically saying that X minus P is always open, but here we're saying this works for any open set and a point contained in it. And the reason why is just you take the complement of this set and you get X minus U union this point, and this is a union of two closed sets, so it's closed. And so if the complement is closed, then the original set is open. The next separation property is called regularity, which says for P in X and A subset of X, which is closed, and P is not in A, then there are disjoint open sets UV such that P is in U and A is contained in V, right? So again, pictorially, if I denote this by P, and for closed sets I like to draw them as like boxes, then we have these disjoint open sets U and V, right? Now, if one thing which isn't immediately obvious is that regular does not imply T1, because the one, like, you might argue that you can replace A with a single point set, right? But a single point set isn't always closed, right? It's always closed if it's T1. So there are examples of regular spaces which are not T1. But if X is regular and T1, then we say X is T3. And you can prove that T3 implies T2, right? Essentially, then, if you know it's T1, then you can replace A with a closed, with a point set, and then you basically have the T2 axiom. there is an equivalent definition for regularity, and that is regular is equivalent to saying if P is a point and U is a neighborhood of X, and remember, neighborhood just means an open set containing P. There is a oh, what? Hold on. My PC just froze there. Are you still here?
Yeah, I'm there.
Okay. Okay. There is a neighborhood V of P such that the closure of V is contained in U. And of course you should go through all the details, but the main idea here is that if you have your point and you have like a closed set, right, A, and then you separate them, let's call this U, and let's call this W since we're using V, right? So how do we construct? So what we do is, so we start with U being an open set containing P, and then we let A be the closed set X minus U. And so then, so really, this is our closed set. And then we use the separation axiom, just the regularity, to construct this is going to be V, and this is going to be W. And this V is going to be the set that you want. So you should prove that the closure of V is going to be contained in W. So really U is going to be the complement. U will intersect W, right? But the important thing is that you're starting with U, and then you construct this closed set X minus U. The next separation axiom is normality, which says that if you start with two closed sets, A and B, then you can find disjoint open sets which contain the closed sets, right? So there's just, again, it's a pretty natural extension of the previous axioms, right? We're just replacing points with closed sets. And so it is important to, again, specify that normal does not imply regular, and normal also does not imply T1. T1 and normal is called T4, as you might be able to guess, and T4 implies T3, again because you can, once you have T1, then you can replace one of the closed sets with a point set, and then you get T3. And analogous to this result, you also have an equivalent definition of normality, which is that your set is normal if and only if for all closed sets A, there is open, or no, and then for all closed A and all open U which contain A, there is an open set V with A is contained in V, and the closure of V is contained in U, right? So again, this is a very natural extension of regularity, where once again we are replacing a point with a closed set. Now the next thing I want to do is talk about how these separation properties relate to the things we've talked about before. Now this question is not in our notes, but I thought I'd mention it, is that T2 and T3 respect subspaces and products. What I mean by this is that if you have a space which is T2 or T3, then any subspace of it is also going to be T2 or T3. And if you have a collection of spaces which are T2 or T3, and you take the product of those spaces, they're also going to be T2 and T3. The analogous results for T4 aren't always true. But again, those are just sort of like pathological things. T3, again, isn't really that often used, but in a lot of upper-level text, you will often be assuming that your spaces are T2. And historically, T2 actually used to be one of the definitions, or like part of the definition of a topological space, because every common example was T2. But that's just a little tidbit. So now we're going to let X be a T2 space. The first thing, and so these next results are going to be about compactness. If A is a compact subspace or subset of X, and P is some point outside of A, then there are open sets U and V with P in U, A contained in V, and these are disjoint, I should say, disjoint open sets with P contained in U and A contained in V. And so this is essentially the regularity condition, except that, well, for one, we're dealing with a T2 space, and here we're dealing with a compact space and not a closed space. So the proof of this essentially goes like if you have your point P and your set A, then for each point in A, you can construct a pair of open sets which separate P and that point in A, right? And so this process is going to create a covering of A, which we can reduce. So covering, and since A is compact, we can reduce this to a finite covering. And then what we can do is take the union. So with the finite covering, we take a union to get V, and an intersection of the corresponding sets, because basically if we reduce this to a finite subcovering, then we strip away the corresponding sets for that contained P, and then we have a finite amount of open sets which all contain P, and if you take a finite intersection of open sets, you get an open set. And since they all contain P, that open set is going to contain P as well. And then they're going to be disjoint because each of those sets that you took an intersection of were all disjoint from all the sets you took a union with, and you can go through the point set details that that construction makes a disjoint pair of sets. The next theorem essentially follows from this is that again, we're going to be saying that x is T2. So if x is compact, then x is regular, and hence T3. And the reason why is that if we start with a P and a closed set A, we have already proven that a closed subset of a compact space is compact, and then we just use the previous result to construct our disjoint pair of open sets. And so this satisfies the regularity axiom, and then we get that it is T3 because we already had that it was T2, and so that implies it's T1, and so if it's T1 and regular, that means it's T3. Again, there's a lot of like technical sort of words getting thrown around, but it's nothing like too difficult. And then the last thing is that if A is compact, then A is closed. And the proof for this, you just want to show that x minus A is open. So again, you basically just start with P, a point outside of A, so a point of x minus A, and then you can construct these disjoint open sets, which means that, which essentially just means that you take any point and then you have an open set which is fully contained in x minus A, and so this implies x minus A is open, and so A is closed. And that concludes this lecture. Do you have any questions?
No.
All right, that's it.